All right, super. So thank you all for coming. We almost finished out the discussion of representations last time. The part that I did not manage to get to was a particular example. So figuring out ultimately the full set of finite dimensional representations of unitary representations of rotations in 2 dimensions. So I thought it would be worthwhile just to review again the big picture. This was useful the last time. Boy, your face is how I feel. Yeah. Yeah. Yeah, believe me. It's bad because I'm usually very good under very little sleep. But I also it's hard for me to judge when I'm not good. And so it's only once I start like making really obvious mistakes and I catch those, I'm like, oh, I'm actually really tired. Yeah. Yeah. It's a bit of a superpower. I mean, really, it is. And for me, it's way better to get 2 hours of sleep than to get no sleep at all, for whatever reason. Okay. Anyway, moving on. So what's the big picture? So we wish to classify all the unitary irreducible representations of a symmetry group under consideration, for example, SON. So that's the big picture. Why are we doing that? We're doing that because symmetry transformations exist. These are translations, rotations, special relativity boosts. We're assuming in this class the world is described by the postulates of quantum mechanics. Yes. Oh, and Biggin, yes. Thank you. Yeah, you're welcome. All right. Symmetry transformations exist. World is given by quantum mechanics. We thus want to be able to describe a general symmetry transformation in our quantum mechanical framework. Very good. All right. Hilbert's fifth problem says that a symmetry transformation is a Lie group. Because our states live in complex vector space, in the Hilbert space, we need a map which is taking us from the Lie group, from Hilbert's fifth problem, to complex vector spaces, and that's known mathematically as a representation. All right. The fundamental building blocks of representations are irreducible representations. That's another step. Statements. Okay. Wigner's theorem tells us that the representations are either linear and unitary or antilinear and anti-unitary. That's coming from the probabilistic nature of quantum mechanics and the fact that we're only interested in the modulus squares of amplitudes overlaps. Okay, good. We'll consider only groups continuously connected to the identity element, and thus we'll only need to consider unitary rather than anti-unitary irreducible representations. A huge bonus of this is that these UIRs will tell us the permitted quantum states consistent with a particular symmetry transformation. So we'll think about that quite a bit in terms of rotations. You've thought about that quite a bit already. So we then are seeking to classify the possibly projective unitary irreducible representations of a continuous symmetry group. How are we going to do that? Within the context of this course, we're going to look only at compact groups, which means we can use the theorem of highest weight. So we seek the representations which take us from the group to the operators acting on our vector space. And we're interested not only in the operators, but even the vector space itself, because the dimensionality of the vector space tells us something very interesting about our quantum mechanics. And the way that we do that is we go up from the group to the generators. We seek the representations of the generators on the operator space, and then we use the exponential map to find in general the representations of our group elements. So in order to classify these representations, we go around the long way along this commutative diagram. And you went through that in, I would say, extreme detail in the homework. And you're nodding, so that seems like a good thing. But let me just pause at this moment to ask if there are any questions on the homework, conceptually or potentially even mechanically. It makes me a little nervous that there are no questions, because either you understood it perfectly or you didn't understand it at all. I'm pretty sure you didn't understand it all, so I'll leave it for now, and if you have questions, you can ask as we go along. Okay, good. We talked about how quantum mechanics is insensitive to phases. And so we have to broaden our allowed representations from beyond just ordinary representations, which are group homomorphisms, to representations up to a phase. We have to allow for projective representations. Math tells us that groups that are simply connected, so any path that is fully contained within the group manifold that can be contracted to a point, that all of those closed contours, all of them can be contracted to a point, that those groups have ordinary representations only, and that all ordinary and projective representations of some group G descend from the necessarily ordinary representations of the universal cover of the group G twiddle. The universal cover has the same Lie algebra as the group G, but is simply connected. So we're guaranteed that all the representations of the universal cover are ordinary. Good. Yes. Good. So an ordinary representation is some, well, a representation is always a map and a vector space. But the difference between an ordinary and projective representation boils down to what's happening with the map. And an ordinary representation, pi is a group homomorphism. What does that mean? It means that if for all elements of our group G, such that G1 followed by G2 is G3, we have that pi of G1 followed by pi of G2 is pi of G3. Good. And then just to complete, if we have a projective representation, then we've got the map pi, the vector space V, and then for us, some phase phi, such that we would then have pi, let's call it in fact sigma perhaps to distinguish. Sigma G2, sigma G1 is e to the I phi G1, G2, sigma G3. Yeah.
And do you only get ordinary and projective representation?
I'm sure you could come up with other maps that have other properties, but these are the only ones that are important for us in quantum mechanics. Great. Good. Other questions? Great. So let's skip ahead. Actually, let's go over here. So we put together a lot of the bits and pieces last time, and then you've also done that in your homework. So I propose that we just skip straight to the example. And if there are questions about what we're doing, then we can go back to that. So in particular, we found the ordinary representations of SO2 last time. And now what we'd like to do is find the projective representations of SO2 and see a little bit about how they work. So all the UIRs of SO2 today. All right. So the manifold of SO2, so the set of all parameters that parameterize the group for the group of rotations in 2 dimensions, what was that manifold? Not S2, because it's 1-dimensional. S1, exactly, yeah. So it's the circle. Now, is the circle simply connected? So, yeah, so the circle is connected, but is it simply connected? So if I take a trip around the circle from 0 up to 2 pi, that's a closed path. And can I continuously contract that path to a point while still keeping the path within the circle? And the answer is no, right? I'd have to like snip the circle. I have to go in the middle of the circle, which is not part of the method, right? So it's even more topologically complicated than SO3, which was if I went around twice in SO3, I was able to contract that path to a point. So what that means is, in technical mathematical terms, the fundamental group of SO3 is Z2. It's a group of 2 elements, 0 and 1. But for the circle, I can go around once, go around twice, and go around 3 times, say in the counterclockwise direction for u. Or I could have gone around once in the clockwise, twice in the clockwise, 3, so on and so forth. And so that's basically clocking integers 1, 2, 3, 4, or -1, -2, 0, and also 0. So then again, the technical term is that the fundamental group of the circle is the integers. So you're not responsible for knowing what a fundamental group is, or the details of that, but again, I just wanted to sort of expose you to that idea. Okay, so the circle, the important point is that the circle isn't simply connected. All right, great. Now the universal cover, because we want to find all of the unitary groups and representations of SO2, we go to the universal cover of SO2, because we know that the universal cover, all of the representations of that group will be ordinary, and I can find all of the ordinary and projective representations of SO2 as it's some algorithmic way from the representations of the universal cover. All right, so universal cover of SO2 is T1, the group of spatial translations in 1D. Let's say spatial translations on R. Why is that group the universal cover? Well, we need to show 2 things. One is we need to show that the group is simply connected. We need to show that the Lie algebra is the same. So well, R1 is simply connected. Is that easy to see? Maybe if it's not, let's just think about the real line. And it's actually vacuously true, right? Well, it's basically vacuously true. So if I have any path that starts at a point and is closed path, I must be going out and then back again, one way or the other. And I'm all within the real line, and then I can just contract any of that extra bit of the path down to the point. So it's simply connected. It's in general, Rn is simply connected. Yes.
If the real line is simply connected, why is the circle not? Like, all the points in the circle.
But maybe look at the circle in another dimension.
Yeah, so we're embedding the circle in R2 in 2-dimensional space. I feel like the circle is not such an easy thing to see as you think about this. I really like the idea of the surface of a donut. I feel like that's a little bit easier to visualize. But if I think about taking a circle around this way, I'd have to cut through the donut to close to a point.
Mm-hmm.
Or like also the other way. Yeah. Yeah. And I don't, this might be going a little too far, but you can think that you can wrap around sort of n times this way, or n times this way, m times this way. So that's a z. You can also go around, so n times this way or m times this way, so that's another z. So the fundamental group of the two torques, in fact, z cross z. Maybe kind of, you can sort of see it, even though I'm obviously not making any kind of math. And so just think of the cross section of the donut. You're very happy with the idea that going around this way, it's not simply connected. Well, the circle is just the cross section of the donut. So it's just the fundamental group is just the integers. And most importantly, the thing that I really want you to get is it's not simply connected.
It is a part of donut.
Precisely. Precisely. Exactly. If I had, say, the two-dimensional disk, solid disk, they would be simply connected. Precisely. Very good. And so because the circle is not simply connected, we should expect that they're projective representations. What, say, Weinberg would call, or I think many people would call, intrinsic projective representations. Okay, good. All right, so we go to the universal cover, which is translations. R1 is simply connected. And so the algebra of SO2 is that of a single generator so the group is the algebra group. The group is necessarily abelian. And the same is true for T1. For the case that you looked at the homework, SO3 and SU2, it was a little bit more non-trivial to show that the Lie algebras were the same. You had a little bit more work to do. You had 3 generators and they were not with computation relations. Here, there's only 1 generator, so there's no computation relations. So the Lie algebra is definitely the same. Okay, good. So therefore, this Lie algebra T1 is the same as the Lie algebra for SO2, which is the same as the Lie algebra for I'm sorry, not SU, rather U1. All right, great. Yes.
Sorry, why does R1 being simply connected when T is T1 is
T1 the group or T1 the algebra?
the group.
Yeah. So yeah, good. You're asking the right question, because if you were asking about the algebra, then I'd be confused. It wouldn't make your question wouldn't make sense. You asked the question that didn't make sense. Good. So the simply connectedness, right? To let me take a step back. Remember that we're always considering Lie groups. So we have not only a group structure, but also a differentiable manifold structure, so that we can talk about things like continuity, things like calculus. And so if I heard your question correctly, which was, why is R1 being simply connected mean that T1 is simply connected? It means that when I talk about the simply connectedness of the group, I'm asking about the differentiable manifold nature of the group.
And R is the manifold of T1.
Yes. Yes.
Well, the manifold of T1 is.
Exactly. Yeah.
Sorry.
I mean, it is like the manifold of T1 is on, just like the manifold of SU2 is the 3-sphere. She showed me detail. Yeah.
Some here we
Good. That was coming from Schur's lemma, which which said that all of the unitary irreducible representations of all the unitary irreducible representations of an abelian group are one-dimensional.
So projective.
Yes. And we'll see that in just a moment. Good. Other questions? And in fact, let me just dive right in because that's really my next point. Oh,
We know XO2 doesn't view.
as groups?
Oh, okay, we showed it previously.
Yeah, so that's true for groups. It's also true for the algebras. Good. So what are the unitary irreducible representations for the group of translations? You've actually already done this. We did this probably day one-ish, right? We said that. So I'm using the tilde to talk about the representations of the universal cover. I'm giving it a hat because these are operators in our thinking about things in terms of objects that act on a vector space. And then it takes a group element, which is given by x being just the position, or rather the amount of actually, let's call it A, because it's a translation by A. We call this e to the I a p hat. So the pth representation is given by e to the I a p hat, where this number A is just a real number. And these representations are classified by the eigenvalue of the momentum operator which is the representation, call it pi twiddle hat prime of P of the generator of translations. I'm going to make this a minus up here, e to the minus I a p hat, generator of translations P. And it's the eigenvalue of the momentum operator acting on the 1D complex vector space spanned by the eigenket P, where we have that, say, our P twiddle hat prime of P acting on P. It's a very complicated way of just writing P hat acting on P. And what do we get when P hat acts on P? We just get the number P back, where this number P is just some real number. So I would like to think that this is all extraordinarily familiar, but perhaps packaged in a way that is a little bit unfamiliar. Yeah, so what I'm hoping will happen for you is that this is going to help sort of map between this area of understanding that you have had already from undergraduate quantum mechanics and then earlier in the semester in terms of the generator of translations being operator, the generator, and the unitary operator that effects translations, which we said was e to the minus I p hat, I a p hat, into this language that we have developed in terms of group representation theory. That's my goal here. And I think what I would like you to think about is how every value of P, which is continuous, in this language is its own one-dimensional complex vector space. That I could think about having a particle with momentum P or a different particle with momentum P1 or another particle with momentum P2, and that all of those different particles are in this language completely different. That under a translation, I'm not going to change the momentum P1 to momentum P2 or back to momentum P. There's an invariance there. And that's what I take as a hallmark of a particle, the invariance of certain properties under my symmetry transformations. Good. Let me pause there. Yeah.
How do you then know that the generator of translations is the or the momentum?
Good. That's a good question. So what we do know, certainly, is that if we think about translations as a group, we know it's a symmetry transformation, we know it's continuous. So we know that the representations are going to be unitary. And we know that we can expand that unitary operator around the identity. So it'll be 1 minus I, A, something, some operator. And I'll call that operator P hat plus order of A squared. Now, what remains to be shown is that that P hat is in fact the momentum operator that we know and love. And that comes from our direct quantization condition, where if I have X as a canonical coordinate, it has a canonically conjugate momentum with a particular commutation relation that XP equals I. And it's that commutation relation that, say, day 1, day 2, we went through that procedure of looking at the commutator and how, if I think about X hat acting on e to the minus I A P hat on the X ket, then that ends up being the X plus minus A ket. I always get the signs mixed up in my brain. But that will allow me then to identify the P hat that lives in the representation theory from the group of translations to the P hat, which is the canonically conjugate momentum to the coordinate.
Remember at the start of this last
Yeah.
Yeah, because you're smiling, you're like kind of stoked about that. Yeah. Yeah. So I think very hard about the problems I give you for exactly those kinds of connections to be made. So I'm glad that you're making it satisfying for me. Cool. And to sort of foreshadow what we'll get to either later today or tomorrow, we're going to do the same thing for time translations. We'll look at the group properties of the time translation operator, look at its expansion around the identity. We will call that operator H, and then we will see that that H will be identified with the Hamiltonian from the fourth postulate of quantum mechanics. We're finally getting to the fourth postulate. Cool. Good. Any further questions on what we've done here so far? Yes. So I guess you would just explicitly, so we're interested in going from, which are the same. And we would like to have some map which is going to general linear group on, I guess, 1D complex vector spaces. So I guess that's just C1. So rather we go up to, right, so this is what we want. Actually, let's try it this way. So this is a sigma, right? Because we're going to expect this to be projective. So in fact, let me draw something else. So this is what's going on in the first homework set of this coming week. which I wouldn't necessarily expect you to understand in full detail, but I think it's helpful for sort of organizing things. So we have what's known as a short exact sequence. Whose details I don't think are that important, but we've got a map which is taking us from the integers into R down to the circle, which is the same thing as R quotiented out by the integers. And then this is inclusion, and this is some projection because the R is the universal cover. And what we're doing here is we would like the representations going from the universal cover R into, again, the GL C1. And we could think about this as going up to, so this is T1, which is the same thing as R, T1 pi prime. And I guess I'm going to call these twiddles because I'm in the universal cover. And then my GL, GLC1. This is again my exponential map. So what we have is our pi twiddle prime of P being the generator. So P lives in here. Goes to a P hat. My P hat lives in here. And then I have that, so my GLC1 basis is given by the P eigenket, where P hat on P is P. And so this exponential map here from the GLC1 to GLC1 takes me from P hat goes to e to the minus a minus IA P hat. Over here on the left-hand side, I would have P goes to e to the minus IA P. And I have that here, P is just a real number. So I have an infinite number of UIRs of 1D unitary representations. Okay, good. But I didn't want, I guess, let's not call this sigma, let's call this pi. I didn't want pi twiddle. What I wanted was pi. So how do I get pi? All right, we're kind of running out of letters here. So we want pi got pi twiddle. And I guess these are all hats. Starts to get a bit busy in terms of notation. But we've also got P, which is the projection from the universal cover of SO2, which is T1. From A, which is an element of the reals. Now, careful, right? The P is an element of the reals, and the A is an element of the reals, and those are totally different, right? Because this P classifies my unitary groups of representations. This A tells me how much I'm translating spatially one of these states in the vector space associated with one of those unitary groups of representations. Okay, so I have a projection from the A element of R to theta, which is an element of 0 to 2 pi. Trivially given by the projection of A is equal to A mod 2 pi. So this gives me this projection from the universal cover to the group itself. Yes. Yeah, it's the inclusive map or inclusion map. Yeah. We're not going to worry about this too much. If you want to worry about it, work on the homework and we can talk about it. There's a lot of beautiful things in there, but for the purposes of what I want you to achieve in this course, it's beyond. Okay, great. So we know how to get from R to S1. That's this projection. Good. But we want pi hat, and we want to get pi hat in terms of pi twiddle hat. So we need to have some way to go from our group up to the universal cover. And that's accomplished with the map, which we call the section, this map S. And remember that the projection composed with the section is the identity map. That's the critical point. So if I start with, say, a rotation by pi over 3, then I go up into R to some value of A, which will be itself pi over 3. This section S is going to be S of theta is equal to theta itself. And then when I take the projection down, theta mod 2 pi, where theta is from 0 to 2 pi, is just theta itself. So this map and this map composed with this map is the identity. So we're good. And this tells us, and I recognize that this is rather trivial, but that's okay. Hopefully it makes it easy for us to understand, okay, so I start with some group element of S1, I take that to a group element of the universal cover, and then I'm able to project that back down. So how do we do this then? So then the representations, pi hat of SO2 are given by the reps pi twiddle hat of T1 by, so our representations we care about are given by the representations of the universal cover of element in the group of the universal cover given by the section of the group element of the original group. And we know that the representations of the universal cover are classified by P. So our representations of SO2 are classified by P. So hopefully this is like either, oh, the sky is opened up and I understand what's going on, or at least is making connections with what you did in detail in the homework, right? In the homework, the question is, what are the unitary groups representations of SO3, which is what you want, but what you ended up doing is you found all the representations of SU2. But how does that help you? It helps you because what you can do is you can go from your elements. So for example, if I is looking at pi of S, this is SO3, which is given by, I need some n hat and theta. This is given by the representations classified again by S of SU2, again of the n hat and theta, where really what I'm doing is I'm really looking at the section n hat theta, where this section S of n hat theta is just n hat theta. So you want this, you figured out these. How do you get from these back to the representation you want? You just need this map that tells you how to go from the group element in SO3 to the group element of SU2, and it is the simplest thing. It's really not complicated. It's probably why nobody, well, if I'm being generous, that's why nobody tells you what's actually going on. Okay. Let me pause there for a second. Yeah.
Sorry, so, the commutative diagram for, you've drawn it for T1 for pi equivalents.
Yes.
But for the SO2, just pi map. That hasn't been connected to.
Exactly. Exactly. Because I'm finding this via this.
Okay.
So I'm saying we want these pi hats. Via this method, I'm able to get the pi twiddle hats.
And then you can get the pi from the pi equivalent.
Yes.
Okay.
Precisely. You're welcome. There are a lot of moving parts.
Yeah.
Yeah. Go ahead, Tian.
Oh, no.
Oh. I guess so. So this is always what's happening behind the scenes. I think maybe I would rephrase your question if it's the right. What you are asking: are there more complicated projections? So are the yeah. I think the sections are always the sections that I've always seen been very simple like this. The projections can be more complicated. So for SU2 and SO3, it ends up being like if theta is less than pi, then the projection is just theta for a given n hat. And if theta is greater than pi, then it's like 2 pi minus theta and then the same n hat. So it's a little bit more tricky, but it's still not so bad. Yeah. But for the next point, which is, I think, really important, you actually don't even worry about any of this, which again, I think is why nobody tells you about it. Again, if I'm being generous, it's why nobody tells you anything about it. And the point is that let's consider two rotations by theta 1 followed by theta 2. So this is then pi hat in the P representation of theta 2, which is following a pi hat in the P representation of theta 1. So what is this? By whatever equation number this is, let's call it equation 1. This is pi twiddle hat P of the section of theta 2, pi twiddle hat P of the section of theta 1. Now, because this pi twiddle is a group homomorphism, this is necessarily pi twiddle hat P of the section of theta 2 plus the section of theta 1. The group multiplication law of translations is just addition. Now, the point is that if I add these two thetas, this might not be some, that it might be a number greater than 2 pi. So if the theta 1 and the theta 2 are, if I add them and it's less than 2 pi, then this is just, so this will be equal to pi p twiddle of just theta 2 plus theta 1 if theta 2 plus theta 1 is between 0 and 2 pi. And everything is hunky-dory. But if theta 1 plus theta 2 is bigger than 2 pi, it's rather e to the I phi p theta 1 theta 2 pi hat of the projection of theta 1 plus theta 2. And remember that that projection involves the mod 2 pi. So this phi p explicitly, this is equal to p multiplying theta 1 plus theta 2 minus theta 1 plus theta 2 mod 2 pi. What does this phi p look like? In general, I have, say, the theta 1 plus theta 2, and say here is 2 pi, here's 4 pi, here's minus 2 pi, and say this is this quantity here. I'm not multiplying by p. Then if I'm between 0 and 2 pi, then I just get nothing. If I'm between 2 pi and 4 pi, then I'll get 2 pi. 4 pi and 6 pi, we get 4 pi. And then if I'm between 0 and minus 2 pi, get, oops, minus 2 pi. I believe this was true last night when I was writing these notes, these lecture notes. Oops, that's not gonna. I'm now in my sleep-deprived state questioning this minus 2 pi down here. I think it's true. I'm not going to be able to think about it carefully on the fly, but it makes sense to me. It made sense to me at 2 in the morning or whatever. But the point that is very important that I want you to see is the discrete nature of this phase. So this ticks around. This phase ticks around as the theta 1 and theta 2 change over. And you might ask the question, well, why am I even writing something with the 2 pi and the 4 pi and so on and so forth? The point is that I could also ask what happens if I rotate again by a theta 3, theta 4, so on and so forth. And then when I look at what happens with the representations of the universal cover, I'm getting theta 1 plus theta 2 plus theta 3 plus whatever, so on and so forth. And that number could become arbitrarily large. But necessarily, in order to talk about the representation of the group itself, whose parameter values are limited between 0 and 2 pi, I will always project down to some number between 0 and 2 pi. Okay, so this is the complicated thing that's happening in the background, which is telling me that if p is an integer, I have ordinary representations, because e to the 2 pi I times some integer is just 1. But if p is not an integer, then I have projective representations. But I'm guaranteed that if I just use the representations of the universal cover, everything will work. And those are ordinary. So I don't have to explicitly work out the details of this phase. So I want to say that here. So notice that once you've obtained the UIRs of the universal cover, may dispense altogether with the reps, the UIRs of the original group. And the advantage of doing that is that the UIRs of the universal cover are ordinary, so life is easy. Good. Yeah.
For the when you edit the phase, it does outside of 35.
Uh-huh.
Wait.
So this phase is specific to the particular representation. Or when I say particular representation, I say, what are the classifications of the representations? And the representations we argued are classified by the value, the eigenvalue of the momentum operator. So it's a little bit weird in my mind. It's a little bit difficult in terms of what you're used to, because this P takes on real values. So I would say, think back to SO3. And there all of your unitary irreducible representations of the rotation group SO3 are classified by all the ordinary representations of SU2, and those themselves are classified by the spin S, which is 0, 1/2, 1, 3/2, so on and so forth. So when you did what you did with the homework, you would think about, so for SO3, you have the pi s of n hat theta. This ends up being the pi twiddle hat s of, again, the section of n hat theta. And so if you ask the question, what is one rotation followed by another rotation in SO3, you go up to your universal cover representation. Like so. Because the representation in the universal cover is ordinary, this is just, let me think about this carefully. This is complicated. So this is some n hat 3 theta 3, that's some complicated, that itself is some complicated function of n2 theta 2, n1 theta 1. It's called Rodriguez formula, from some guy in some ancient time. Somebody figured this out from trigonometry, like it was brutal. Much easier to use modern techniques. But in any case, so there's some single axis and some single angle that corresponds to this rotation followed by this rotation living in SU2. And then this is necessarily an ordinary representation. And if you demand to project down to the representation of SO3, which I highly discourage you from doing, but you can, then you will get pi hat s of the projection of n3 theta 3. And if this theta 3 is between 0 and pi, you're fine, you don't pick up a phase.
Oh, wait, I think.
Let me just finish the statement and then we'll come back. Yeah, so I'll say it this way. So this, if 0 less than equal to theta 3 less than pi, otherwise it's going to be e to the I some phase that depends again on the spin s, which depends on n2 theta 2 n1 theta 1, and then pi hat s of the projection of n3 theta 3. So in fact, this is not even a projection, it's just n3 theta 3 here. Otherwise. And this phi s, if s is integer, is just 2 pi.
Right. So you lose the phase.
I'm sorry?
So you lose the phase.
Correct.
Yes.
So that the representations of SO3 when s is integer are ordinary representations.
That's why we.
Exactly. But we have to keep them, we have to allow for them. And the result is that electrons exist. Yes.
I was just going to say earlier, when you wrote down other SU,
Yes.
when you then split it up with the curly brackets,
Yes.
I was confused that the second one is just a pi. It's not
Yep.
pi four.
Correct.
I thought it was.
Yeah. There are a lot of little things. Yeah. Good. Okay, so let me make sure I understand your question. So I think your question is why can I have any value of spin for SO2 and not for SO3?
Is it because of the universal?
Um, yeah. I wouldn't say that you're using the theorem of highest weight to find that the UIRs of SO3 are classified by a discrete number. Rather, the UIRs of SO3 are a discrete, countably infinite number. And you use the theorem of highest weight to find what those values are. Yeah. Yes. So let me say we're not yes, definitive yes. Let me give a strong tentative yes. Yes, I think you've put your finger on why. So we know that we need to go to the universal covers for both cases. And so then your question boils down to why do the UIRs of the translations in one dimension have an uncountably infinite number of UIRs versus SU2? And I think I have a strong suspicion that you're right, that it's about the compactness of the. Good. How are we doing? No complaints. All right, so moving on. So I just want to make a couple of other statements of interpretation of what we found. Okay. So as mentioned, so I guess while I have I've used P to classify the UIRs of T1, and then that's natural. I've continued to use P as a label to classify the UIRs of SO2. But this P is really the intrinsic spin of a particle. I don't know how to write to go like pi hat of S equals pi hat twiddle of P, where S is P, like that. Yeah, good, thank you. So as I said before, but I'm now writing it down, for P in the integers, the representations are ordinary. One thing that's interesting here, notice that the spin plus one is a different particle than spin minus one, even though the magnitude of the spin is the same. Yeah. All right, so we call particles whose states live in these UIRs bosons. For P and Z, P and R, P not in Z, the representations are projective. For P half integer, we call the particles fermions. All other P are called anyons. Running out of names. Bosons obey Bose statistics. Fermions obey Fermi statistics. Anyons statistics smoothly interpolate between Bose and Fermi statistics.
So if we looked in 2 dimensions, how long was 2 dimensions? We would have anyons, bosons, and because we're in 3 dimensions. We can find
Precisely. Yeah. Sorry, what was your question?
That's my.
Yeah, so they do exist. Yeah, but as mentioned, only in systems that are restricted to 2 dimensions. Well, in some sense, it's sort of more natural, right? Because we're used to continuous spectra. Yeah,
Instead of this maximum.
yeah. Good. That's what I wanted to, well, I guess, I mean, so just to write it down, right? So for homework, note how different SO2 is from SO3. The only possible potentially projective UIRs of SO3 are discrete with spin equal to 0, 1/2, 1, so on and so forth. With no possibility of negative spin or non-half integer values of S. Also, in fact, the phases for the projective representations in SO3 are simpler than the phases of SO2. And this comes back, so the phases in SO3 can either be +1 or -1, whereas the phases in SO2 can be any wild value of some real number p multiplying some integer. And yeah, so I just want to say that. Yes. Oh, no,
There's one.
sorry. Yeah. Great. That's what I wanted to get to in terms of representation theory. This is not easy. Yeah. I hope that my goal would be obviously that you understand everything perfectly. It's not realistic, but I would like to think that you're not lost, which I think is true. And we'll move on. The plan is to move on from here to time evolution. But we can circle back to this at any time if you have any questions that come up as you do homework or as you process what we've been talking about. Yeah, great.
Was this math and stuff done after the discovery of spin?
So I think that it was all really settled with Bartman's theorem, which we haven't talked about, but is referred to in the first problem of the homework. And Bartman's theorem tells you when you have intrinsic projective representations. And that was, I want to say, the 50s. And I would say even further back, you'd have to go to Wigner's theorem. So actually, I mean, really getting down to brass tacks, I think your question was, which one first, spin or the understanding of quantum mechanics? And that's basically what your question is. And spin was very much way before quantum mechanics, right? Spin was one of the, so the Stern-Gerlach experiment was one of the major stepping stones that was needed in order to spur the understanding of quantum mechanics. And it's really the spin 1/2, which tells you that you have to allow for complex vector spaces, which is totally nutty. Right? Everything in normal everyday life tells you you only need real vector spaces. So it's very, very different tuition involved. Totally. It's wild. Super duper wild. But I'm glad you're getting an appreciation for that. It's definitely one of the goals here. Good. Last questions. All right. Let's make things move through time. All right, time evolution. All right, so recall our fourth postulate of quantum mechanics. Which is that I partial t on some state psi, which can be a function of t. This is equal to the Hamiltonian operator acting on psi of t, where the Hamiltonian operator itself may depend on time. I'm starting new numbers. I don't remember what my numbers were. Let's just start fresh now that we're in a fresh section. Let's define the time evolution operator. Such that psi at time t is given by time evolution operator, which is a function of the initial time t0 and the final time t, acting on the state at time t0. So in words, u hat of h hat of t0 evolves the state psi of t0 ket to the state psi of t ket. And the notation is again a bit heavy because I have a hat over the letter, which is indicating that this is an operator acting on our Hilbert space. I have a subscript, which is an h hat, and that indicates that this is time evolution with respect to the Hamiltonian of the system. Now, you might say, why am I being pedantic about this h? Well, it will turn out in quantum 2 that it'll be valuable to time evolve parts of the system according to, say, the unperturbed Hamiltonian and other parts of the system according to the perturbed Hamiltonian. So it's good to keep track of what you're evolving with respect to. So forgive me the heavy-handedness in the notation. Currently, it will hopefully pay off as we move forward. Let's talk about the group theory of time evolution. And I'm putting this in not to be like, oh God, group theory, not again, but rather my goal is that this will tie in very nicely with what we just talked about. So this will feel like a very natural way to think about time evolution. So time evolution, and sort of as mentioned before earlier today, this is now completely independent of our statement about the fourth postulate of quantum mechanics. But we will use the fourth postulate of quantum mechanics to connect the generator time evolution to the Hamiltonian, as mentioned earlier. All right, so time evolution is a continuous symmetry. So hence, this UHT0 is a linear unitary operator. Hence why I've written it as a U. So we must have that UHT0 permission conjugate is equal to UHT0 inverse. So it's equation 3. We also have that So let me ask you, what is the time evolution as an operator, which is taking my state from time t0 to state time 0? Say it louder.
The identity.
It's the identity. Awesome, thank you. We also have the composition rule for time evolution. So suppose I evolve from time t0 up to time t1, and then I evolve from time t1 to time t2. What do you think is the total time evolution operator? What does it take me from, and what does it take me to? Yeah, t0 to t2. Very good. Finally, suppose I'm going from t0 to t, or rather, let's call it t1 to t2. And I am considering the inverse of this. How would I write this as an operator in terms of the t1 and t2? Right, this is t1, t2. And perhaps you can see that from, say, of t1, t2, which is following a t2 to t1. From 4b, this is of t1 to t1, but that's the identity by 4a. Good. Any questions? Great, thank you. All right. We may expand infinitesimally close to the identity. So if I imagine going from t0 up to t0 plus epsilon, it's be 1 minus I epsilon, some operator that may depend on t0 plus order epsilon squared. So we'll see, as I mentioned before, but we'll just write it down here. We'll see in a moment that the generator for time evolution defined here as h hat of t is the Hamiltonian h hat of t as given by the fourth postulate. Mechanics. All right, so let's call this 5. All of this should be old hat at this point, and I'm not, yes.
Sorry, why do we say minus not plus?
If we made it plus I epsilon h hat, then the h hat in this would be minus the Hamiltonian.
Oh, right, because wait, in the past.
I may be switching conventions.
Okay.
But I can tell you for sure here that this will give us the right sign for the Hamiltonian. Yeah, there's a certain amount of ambiguity with some of the signs from the symmetry groups, and sometimes if there's no ambiguity, I would claim at least here there's no ambiguity. Okay, good. Other questions? I know, and I apologize if I'm switching up signs, and I'm apologizing if I make a mistake with signs. I know when I was a student, I was maddened whenever the professor made a mistake. dude, your only job is to get this right. And A, that's not true because we have many hats we have to wear. And B, signs are very hard. Yeah. So I do my best. I apologize if I make a mistake. Yes.
So you still would.
Oh, yeah.
Generally would be H.
Okay. So that's a good question in terms of, let's just call that as a question of units, right? So this identity operator is going to be unitless. This I claim is a Hamiltonian, which will have units of energy. This epsilon is going to have units of time. And so there's going to have to be some over something, which tells me that this combination is unitless, and that's going to be h bar, which we set to 1. Yes. In exactly the same way as when we looked at translations and we had A and P hat. Good. Any other questions? Wonderful. All right. We can go a step further in time to find, say, the time evolution operator, which takes us from t0 up to t0 plus 2 epsilon. So this is the time evolution operator from t0 up to t0 plus epsilon, followed by the time evolution operator from t0 plus epsilon up to t0 plus 2 epsilon. And we can multiply this out. So this second time evolution operator from, say, equation 5 tells us this is 1 minus I epsilon h of t0 plus epsilon. And then expanding the first time evolution operator, it's the same as what we had from equation 5, 1 minus I epsilon h of t0, all plus order epsilon squared. Notice that I'm allowing my generator time evolution to itself depend on time. You might say this seems like a bit artificial, and for many problems it is. But you could also imagine, for example, I've mentioned this before, say an electron in some kind of magnetic trap, and I apply a time-varying magnetic field to that electron. Good. So I can continue this process up to a finite time translation from t0 up to t. It has to be the limit as capital N goes to infinity of the product, little n goes from 0 up to capital N minus 1 of one operator minus I t minus t0 over capital N, Hamiltonian evaluated at t0 plus n times little n times t0 t minus t0 over capital N plus order epsilon squared. This equation, which I'll call equation 6. So there are 3 cases to consider for 6. So the first case is if the Hamiltonian is time independent. So what does this look like to you if this Hamiltonian does not depend on time? Yeah, exactly. Not a trick question. Exactly. Then this time evolution operator is e to the minus I t minus t0 multiplying the Hamiltonian. Let's call this 7a. Second possibility, if the Hamiltonian depends on time. But the Hamiltonian at different times commutes with itself. So what do you think would be a natural generalization of 7a if this Hamiltonian depends on time? Yeah, I'll definitely have a time dependence. So I'll have an h that has some kind of a t. But it better be in this more complicated case such that when the Hamiltonian is time independent, I reproduce the previous results. Maybe I'll just write it down. I'm not sure how to motivate it further than that. So I'm going to integrate my Hamiltonian. Okay. So this should all feel quite reasonable and involves objects that you have definitely seen before. The last possibility is the most complicated one. If h hat of t depends on time, but the Hamiltonian does not necessarily commute with itself at different times. Now we have to worry about the ordering of these operators that we see up here when we went 2 infinitesimal steps, that the Hamiltonian at the earlier time is to the right of the Hamiltonian evaluated at the later time. It's a time ordering. So then what we introduce is what's known as the time ordering operator acting on the exponential. So sometimes people include the curly braces to make it clear what is included within the time ordering operator or the time ordering symbol. I will, forgive me if I start dropping the curly braces. To me, it's fairly obvious that everything to the right of the time ordering symbol is time ordered. Yes.
Is the arrow in T part of the equation?
Yes. So you could have time ordering in the other direction, but let me first define this time ordering. Okay, so this T symbol with curly brackets is defined. So actually, sorry. So this is time ordering. It's often called operator. It's also often referred to as symbol. Operator might be a bit confusing because we often refer to operators as those objects that act on vectors in the complex Hilbert space. This is not there's no hat going on here. What this is telling me is as follows. So it's defined such that all operators inside the curly braces are ordered such that the operators evaluated at later times are all to the left of operators at earlier times. All operators evaluated at earlier times. So in particular, so time ordering of some operator O T1, O T2 hat, this is O hat T1, O hat T2 if T1 is bigger than T2, but is equal to O hat T2, O hat T1 if T2 is bigger than T1. And maybe let me really make this more obvious. So this is operator 1 at time T1, operator 2 at time T2. So this is on the right, operator 1, then operator 2, and then it's operator 2, operator 1. I could also use completely different letters, operator O hat, and then your favorite other letter. I'm not sure. M, N, P, whatever. Point being that this time ordering symbol is freely moving these operators past each other, irrespective of commutation relations. That's what I want to emphasize. So then we should think about what this is. Sometimes it's written this way. That I write EXP rather than E to a thing. I'm sure you've seen that before. So this is a time ordering operator. Curly braces. All right, so the exponential I can expand. So it's the identity operator minus I integral T0 to T dt1 Hamiltonian T1 minus a half integral T0 to T dt1 integral T0 to T dt2 Hamiltonian T1 Hamiltonian T2 plus 1 plus I over 6 integral T0 to T dt1 integral T0 to T dt2 integral T0 to T dt3 H T1 H T2 H T3 plus so on and so forth. I'm sorry that I bore you. What does this time ordering operator do? It forces, so for the identity operator, it doesn't do anything. For the single operator, the Hamiltonian, it doesn't do anything. That's nice. But as soon as we have two operators, this time ordering symbol is going to make this Hamiltonian of T1 to the left of the Hamiltonian of T2, so long as T1 is bigger than T2, where I'm integrating both T1 and T2 over the same interval. But if I'm in the region of this interval, this integration region where T2 is bigger than T1, then the H T2 is going to be to the left of the H of T1. So I can enforce that specifically by restricting my integration region of T2 to always be less than T1. Notice the upper bounds. Up here with the time ordering symbol, my upper bounds are T, with my lower bounds being T0. Here now, my upper bound for T1 is T, with a lower bound of T0, but my upper bound of T2 is T1. So my T2 is always less than T1. And so then I get Hamiltonian T1, Hamiltonian T2. Notice the combinatorial factor is gone. So I've cut out half of my integration region by restricting T2 to be less than T1. Just think about the square of T0 to T1, I'm sorry, T0 to T for T1 and T2. And I'm cutting half of it out. So I'm absorbing in some sense this 1/2 in restricting my integration region, which then leads me to this ordering to the left, H of T1 followed by H of T2, getting rid of the time ordering symbol. Then my next term would be plus an I, integral T0 to T dt1, integral T0 to T1 dt2. And then what do you think the limits of the integration for the dt3 integration region are? Perfect, T0 up to T2. So I've got my Hamiltonian at T1, where T1 is always bigger now than my Hamiltonian evaluated at T2, and T2 is always bigger than T3. And if you think about now a three-dimensional cube and the sort of parallelepipedy thing that comes from this particular ordering, then you can convince yourself that the 1/6 again gets eaten. Where the integration limits in 8 guarantee that the Hamiltonians are correctly time ordered. Note that the combinatorial factor one over n factorial from the Taylor expansion of the exponential I'm not sure has been absorbed or is accounted for in 8. Okay. So where do I have this? So 7b, and this is called this 7c. Notice that 7c and 8 reduce to 7b for h hat t, but h t1 commutes with h t2. And that 7b reduces to 7a for h hat t independent, as we would definitely demand. Sure. So let me make a note where you can have a resource to take a look after this also. Combinatorics. Oh my gosh, my handwriting. See also Peskin, page 84 to 85. But consider the integral t0 to t dt1, integral t0 to t dt2, the Hamiltonian t1, Hamiltonian t2 with a factor of a half. So this is supposed to be a square. So this is, say, t1, and this is t1, this is t2, going from t0 up to t0 up to t. Exactly. So if I simply restrict t2 to be between t0 and t1, so this now is integral t0 to t dt1, integral t0 to t1 dt2. And you can draw a similar picture in 3D. 4D is a little hard. Yeah, very good. All right. I'm -2 minutes left in class. But I want to write one more paragraph. So this finishes the Lie group theory aspect. And I want to say then, so the solution of the postulate PDE. So in the homework, sharp nose intake triggered, you'll explicitly show that the definition of U hat A hat Q hat H hat T T0 as the time evolution operator, which is say UHT T0 psi T0 is equal to psi of T, means that UHT T0 itself obeys a time-dependent Schrödinger type equation. You will further show explicitly that the solutions 7a up to 7c that we wrote out, or not the solutions, but the equations 7a to 7c explicitly solve such a PDE. And therefore, it's the fourth postulate that allows us to identify the generator of time translations from the infinitesimal expansion of the time evolution operator here, the identity with the Hamiltonian. At the risk of overloading you, we need the fourth postulate because in non-relativistic quantum mechanics, we are explicitly treating time and space differently. That we are explicitly treating space, or rather we are elevating space to an operator. So our generalized coordinate, or our coordinate x, goes to x hat with a canonical conjugate momentum p that goes to p hat. However, we are not elevating time to an operator. So even though you can think about time as an operator and has a canonically conjugate momentum, which is the Hamiltonian, and then you can apply straightforwardly the direct quantization condition. Commutator T hat with the Hamiltonian is I. That's not the perspective that's traditionally taken in non-relativistic quantum mechanics classes. And this is what one has to fundamentally grapple with in a course that considers both, or tries to find a theory that is consistent both with the postulates of quantum mechanics and the postulates of special relativity. And one option is to elevate time to an operator, as I've mentioned. And this would be a sort of string theory-like approach. The other option would be to demote position to a parameter, just like time is a parameter. That would be the field theoretic approach, that you have fields that are functions of the parameters of space-time, where the fields are operating. But the space-time parameters are not themselves operators. But I just wanted to have those words in your brain. Good. And yeah, and just to be clear then, so if you take one or other of those more self-consistent ways of considering time and space on equal footing, you no longer need the postulate. Good.
When you spoke earlier about the, could you just scroll up to talk about the pages in time order? Yeah.
So this is where I first mentioned the time ordering, and then I can show what the time ordering symbol does with the exponential. So do you want here or further down?
Further down.
Diagram. Oh, yes. Mhm. So I'm saying that my T2 has to always be less than T1. So if my T1 is, say, 2/3, then my T2 can be anywhere between 0 and 2/3, but cannot be beyond it.
And you do the math, it works out.
Correct. And so hopefully here you see it explicitly for the two. Yeah.
Yeah, it's hard vision.
Correct. So you can take my word for it, or you can give yourself a problem.
I'll take
Yeah. Combinatorics is also not my strong suit. Yeah.
In the more field theory approach that you mentioned, where you have a field operating a position, you then also have a canonically conjugate field that's in terms of momentum. Or is there
You're
Yeah.
almost there. You're almost there. So you say that my field is phi hat, which is a function of x mu time and space. And there's a canonically conjugate momentum pi hat, which is itself a function of, again, space-time position. X mu. So there was the optional problem with the Poisson brackets, where we talked about the Poisson bracket of fields. And then that carries over to the from the Dirac quantization condition, a commutation relation between your field and its canonically conjugate momentum. Now, remember that in classical mechanics, if I have a point particle, my Lagrangians in terms of, say, x and x dot, time derivative of x, and the momentum is defined as the derivative of the Lagrangian with respect to x dot. So the same thing carries over to fields. I write a Lagrangian in terms of phi hats, or phi's and d mu's of phi's. And then the canonically conjugate momentum is the derivative of the Lagrangian with respect to d by dt of phi. So there's this entirely equivalent way, for example, of deriving Maxwell's equations in terms of fields. When I taught it, I called it fields capital Q and capital P. And you can derive the Maxwell's equations from the Poisson brackets of the Q's and the P's. Yeah. So, and this is what people were thinking about in the early 20th century. So how do we, they're like, look, I've got quantum mechanics, non-relativistic quantum mechanics, and that gives me the hydrogen atom. But that only gives me the stationary states of the hydrogen atom. But we actually are able to observe the energy levels of the hydrogen atom from the light that's emitted when the hydrogen atom de-excites. And I see those discrete quanta of light as discrete packets. And so it stands to reason that not only should I quantize the electron, I should also quantize the field. And so people were from the very beginning thinking, how do I quantize fields? And the the prescription for quantization comes from the positive quantum mechanics, which is the Dirac quantization condition, where I take the classical Poisson bracket and I turn it into a commutative. And so people were thinking from the very beginning about the Poisson bracket technology applied to fields and taking that over to computators.
That's why you get scary stuff when you Google Dirac quantization. Only field theory stuff possible.
Oh,
I mean, I don't know what to say.
I don't know what your cookies are doing in Google, it says that that's coming, I don't know. Yeah, maybe show that to me today. Okay, I'm happy to keep hanging out here answering questions, but people, I think, have to run to mail. Thank you very much.